Wasabi, you guys. Silver here, and we are going to start our integration bee training for advanced. I'm a little excited for this series because this is where the fun stuff begins, where we can sort of handle MIT level integrals. Now, in this first section, we're going to learn about King's rule, which is the most important technique that you must learn and to be comfortable with in order to learn other advanced techniques like pretty much like any other definite integral tricks. So let me first teach you the concept of King's rule. So in King's rule, we'll have an integral like this. And in your calculus textbook, you probably see this before, but never really used it. Now, in the calculus textbook, it only told us this formula here, that f of x is equal to the same function but with a plus b minus x, where a and b are the bounds. Now, I won't blame you. I was one of those students that kind of ignored this formula. But now that we're here, where we want to do speed integration at an advanced level, this is probably like the number one key to handling very difficult, awkward, definite integrals. And this is the start of King's rule. So let me show you the actual integral form that we will always come across. This is the type of integral that we will be dealing with. This is where we use King's rule and how we notice it and how we solve this type of integral. Now, let me first show you why this formula equals. So pretty much what we're doing is we are letting u equal a plus b minus x. That's all we're doing. It's just a u substitution. And then to solve for x, it's just a plus b minus u, which is how we got this. Wait, but that's not u, right? Well, let me show you another thing. When it comes to definite integrals, it doesn't matter what the variables are, right? We have this integral, and let's say we have this integral. Okay. If the functions are the same and the bounds are the same, then they are equal. You can interchange variables. It'll still be the same answer. Okay. I'll explain more thoroughly as we use the example problems. So here is what we're exactly doing with King's rule. So whenever we see an integral that's in a form of this, we use u equal a plus b minus x, or the addition of two bounds and then minus x. And what this would give us is a, because if you plug in a, you get b, but remember that this negative is going to switch the bounds, and so we're still going to come up with a from a to b. The bounds are going to become the same thing pretty much. So as we have that, now x is equal to a plus b minus u, f of u, or I guess I'll go ahead and just format it like this, just for ease. And this is what we had. Okay, now again, u and x, they're just variables, right? It's just kind of like f of x equals x, f of u equals x. F of u equals u. Are they the same function? Yes. It's just different variables. So now, here's where it'll get a little uncomfortable for you. So, we're going to let this equal to I. Okay? And now, because this is equal to I, this is equal to this, which also equals to I. Okay? So what we're going to do, but pretty much what I'm going to do is I'm going to let I plus I equal 2I, right? However, for each I, we're going to use different forms of I. We have this and we have this. Again, these two integrals, they equal the same thing. Okay? And the reason is because these bounds are the same. This is what makes the definite integral is what makes it equal the same value, right? If it was indefinite integral, then these two integrals would not be the same, right? I just want to clarify that. Like, for example, like if I had something like this, right? I'm sorry, like this. Right, and then if we do a u substitution, right, we do a u substitution, and we got something like this. Are these two integrals the same thing? No, they're not. Right? These two integrals are not the same thing. They are not equal. However, if we put in bounds, if we plug in bounds, are they the same thing? Yes, because they both equal the same real number. Okay, that is why we are allowed to do this. Okay, so now when we let I plus I, so we technically have 2I equal from A to B, because they both have the same bounds, we can combine them and we can interchange u back to x and still equal the same thing. So we have f of x plus f of a plus b minus x plus, and then we have this. Again, we can interchange. They're just variables. So we can do this, right? They equal the same value as I because we have bounds, right? Now, if you add them up, what happens? F of x plus f of a plus b minus x. What's our denominator? F of x plus f of a plus b minus x. They cancel out. So what we have is 2y equals from a to b. This all cancels out to 1 dx, right? If you put them together, because they both have the same denominator, so we can combine it together, and it cancels out, right? I guess I could just write it quickly here. They have the same thing, right? F of a plus b minus x, and then they have the same thing here at the bottom, a plus b minus x plus f of x, right? They're the same thing, they cancel out. See, so we get 1. And then, of course, you just integrate this and you get b minus a. Okay, this isn't your answer. Be very careful. This is not your answer. This is 2y equal to b minus a. We want to solve for I. So what this means is that your integral is equal to b minus a over 2. And this is your solution. Okay? Again, we're gonna do this a lot so that you get comfortable interchanging variables. Okay? I know it looks illegal, but again, we can do this because this is a definite integral. If this was indefinite, if it didn't have bounds, then yes, we are not allowed to interchange variables freely like this, right? Just like how I explained here. This is only equal if we have the bounds. The bounds can be different as long as the u substitution correlates, right? So if I had something, I'll write at the bottom. Like if I had something else, let's say, like for example, some function e to the x, e to the negative x, I guess, right? And of course, like they don't equal each other, right? I'm gonna put e to the x here. And so like they don't, let's say like they don't equal to each other for some reason. But here we have like from 0 to infinity. And then if you let u equal e to the negative x, you will get, let's see, I'll just simplify 0 to 1, right? Of course, again, these two integral, they do indeed equal the same thing. They equal the same thing. Okay, this integral is equal to this integral. Okay, which means that we can go ahead, which means that we can go ahead and cover this as x. And they equal the same thing, right? The same value, as long as the u substitution correlates. All right, let's get more comfortable with this, shall we? This looks suspicious just a little bit because we have this and this equal the same thing, and then plus something else. Okay. We can sort of simplify this just to ease our mind. Let u equal x plus 2. And when we do this, we get 5. This would be 9. Let's see, this would be ln of u plus ln, let's see, what would this be? U minus 2. X is equal to u minus 2. So u minus 2, 14. 14 minus u. Okay. Is this King's rule? Yes, it is. Because notice that 9 plus 5 is equal to 14. And it could actually be very nice to fit here from 14 minus u. Okay, so I guess we know what to do. We're doing King's rule. In fact, I could go ahead and interchange the variables right now. This would still equal the same thing. 5, 9, ln of x. They still equal the same value. They equal the same value. So I can go ahead and just interchange my variables. Okay. Again, I'm going to repeat. You can only do this for definite integrals. Okay. So now that I have that, now we can go ahead and go straight up into King's rule. Okay. Let u equal 14 minus x. We already know what we're doing. We already know what we're forcing this to become. The bounds stay the same. We get ln 14 minus u, ln 14 minus u, ln of u. And of course, if we let this equal to I, this is I, then this is also equal to I. And so what we're doing is we let I plus I, we get 2I. So 2I gives us from 5 to 9, ln of x. Well, they both have the same denominator, so we can just combine them. And plus ln of 14 minus, again, interchange the variables because they equal the same thing. As you can see, they just cancel out. So we have 1 dx This is equal to 9 minus 5, 4. 2y is equal to 4. Therefore, our integral is equal to 2. And that is our answer for this integral here. Okay? In fact, if you do this a lot, you can easily get a sense like, oh, okay, this is King's rule, this becomes 7 minus 3 over 2. And that's like your answer. You know, don't be careful though. Sometimes you have to make edits, sometimes you have to modify, etc., and then kind of go from there. Okay? Go ahead and give it a try. Go ahead and use the King's rule and see what see if you can understand the concept of the King's rule. So, of course, I'm gonna go ahead and just go through. Of course, this you can easily see that this is King's rule just by looking at 2012 minus x and the symmetry here. So of course we know, okay, well if we do 2i, you know, letting u equal 2012 minus x, it's gonna sort of do a reflection, and this would give us 2i equal to from 1 to 2011. So 2y equals 2. So once we get that, we get 2010, 2011 minus 1, and now I is equal to 1005. So this is what it would look like when we're speed integrating. So of course, we could even do it mentally too, like 2011 minus 1 divided by 2. Right. Again, don't always do this though. You just have to be very comfortable, and you have to be very sure that it's just this, or maybe there's something else that you have to do. Okay? But for now, it was very clear that this is just King's rule. Okay? Let's do more examples. So this one's from Harvard MIT Integration B. And can you see what is very suspicious about this? So, what do we do here? If we let u equal 2018 minus x, then we get what? 2017 is 1. 2018 minus 1 is 2017. This will give us du equal negative dx. So this negative is going to fix our bounds. So our bounds become the same. However, we end up getting 2018 minus u over u du. Okay. Interesting. What do we do now? What do we do now? So I'm throwing this integral at you because, like I said, I need you to get very comfortable with interchanging variables, as well as learning to add integrals to itself. So of course, this is equal from 1 to 2017, ln of 2018 minus x over x dx. And so now if I'm going to let this integral equal to I, then this is also equal to I, because they're both the same integral, right? They correlate to each other. They equal the same value. So 2y gives us from 1 to 2017. We can combine them because they have the same bounds. Okay, if they don't have the same bounds, we can't combine them and we're kind of stuck. But because they have the same bounds, we can go ahead and just combine them freely. ln x 2018 minus x plus the ln of 2018 minus x over x. And what does this equal? By logarithm rules, we can combine these and they just equal to ln of 1, right? And ln of 1 is equal to 0, therefore this is equal to 0. If 2y is equal to 0, then this whole integral is equal to what? 0. And that's just our answer. Okay? Alright, we're getting very comfortable with King's rule now. That's very good. We're starting to get get further into some more advanced definite integrals. So what do we do here? What do you think? What do you think we should do? How do we speed integrate this? Maybe I feel like in most integration bees, they'll probably rewrite it like this, just to scare a lot of people. This is called stunning a competitor, right? The way you form integrals differently makes a huge impact, because even though they're the same integrals, making the integral uglier, forming it uglier, causes the competitor to hesitate a little bit and waste time. So that's called stunning. You stun speed integrators like this. But I feel like a lot of, maybe most integration bees might rewrite it like that. But for now, for the sake of this training, now that you're aware, we'll just leave it like this. Okay? So let's go ahead, maybe simplify this. Or maybe this is simplified, but we could maybe separate it, right? What if maybe it might be in King's rule? ln x plus ln of 1 minus x. Okay. So what now? Is this King's rule? Yes, it is. This is indeed King's rule, right? You just let u equal 1 minus x, and it reflects. And so, of course, this is just going to equal, 1 minus 0 over 2. This gives us a half. And we're done. See, there you go. Look how fast we just solved it, right? Impressive. Very, very useful. It's very important that you get super comfortable with the King's rule. Okay? And if you can do it mentally, then that's a very good thing. It's a very good thing. If not, that's okay. You could just rewatch this whole entire video until you become more comfortable with it. Maybe try the integrals yourself and see if you can get to the right answer. Oh God, what is this? This looks awkward, right? This definitely does not look like King's rule, because we have a weird looking x on this power here. So what do we do? What do we do? Well, we start slow, well, not slow, but like take little steps. Right, let's take little steps. Maybe, let's see, this is x to the power of x, 1 minus x to the power of x. Huh. Interesting. Okay. But what if we do divide top and bottom by x to the power of x? So divide. So what we're doing is we're going to divide x to the power of x, divide x to the power of x, divide x to the power of x. So what we're doing now is we have 1 minus x, 1 minus x, and now we're just left with 1 minus x to the power of x. Aha! Now what does this look like? What does this look like? This is King's rule, right? If we let u equal 1 minus x, again, we could just go ahead and interchange the variables. You don't have to turn it back to u. It's just a guideline, not a guideline. It's just a guidance. We just put this as guidance. We just write it as guidance, and then, of course, we get 1 minus x to the power of x, right? Aha! And then, of course, we add this integral and we add this integral, and this gives us 2y. Right, the denominator is the same thing. As you can see, this will definitely cancel out to each other, and this cancels out, of course. This is equal to 1. So our integral is equal to 1/2. And we're done. You see? Beautiful. Great. Cool. And that's it. This is the basics of King's rule. It does take a lot to get used to because, again, this method is not normal to do in calculus, right? So it takes a lot to get used to. So definitely get comfortable. Rewatch this video and try doing the integrals on your own and see if you understand the process of King's rule. And once you understand the process of doing it by hand, then you can try doing it faster and you'll develop a sense of King's rule and you'll be able to actually solve it mentally, okay? Which is very powerful. So that is it. That's it for this section. I also forgot to mention, I'm gonna do this advanced series a little different. I'll be splitting it a lot more into sections because don't get me wrong, the previous trainings was it was a lot of long videos in which I had no choice. So because we are in advanced level techniques, of course integrals are a lot harder and they will take a lot longer. So I will be splitting the series into subsections. So like in this video, we only learned the beginning of King's rule. The next section, I'll be teaching you all different kinds of sneaky King's rule, not including Queen's rule, which is like u let u equal pi over 2 minus x or trig stuff. But with other cases of King's rule like this, smaller details and stuff. So I'm excited for that. And yeah, stay tuned. Definitely subscribe and turn on that notification so that you won't miss out. Okay? So thank you guys so much for watching. I'll see you guys in the next training video. See ya.